What's up, guys? Teef right here, back with a projectile motion lab, lab 2 in physics 2111. So let's get right into it. Introduction. The purpose of this lab was to analyze how a projectile's position in both the x and the y direction is affected by gravity and drag, both in an experimental sense and in a computational sense. So this basically just meant that we threw a paper ball, we had that experiment, we had experimental data, and then we made a computational model of the same experiment and then compared the two data. So the model slash fundamental principles used, F equals ma, or mass times acceleration, was used. Acceleration in this case is g, and that's kind of shown in this free body diagram here. It's the only thing acting on the object, and that's Newton's second law, and it's a fundamental principle. And then glow script, tracker, and Excel were all models that were used to create graphs of real and computational data. Within GlowScript, the position update formula was used and the velocity update formula, in which this case right here, the force over m, or the acceleration would just be that g. So a little preview. The results indicate that the gravity-only model that was generated was perfectly parabolic, while the computational model that includes drag was much more accurate with the data collected experimentally. So this will be shown kind of later when the graphs are shown, but without any drag acted on it, the ball went much, much further than it actually went in real life. And then this shows that drag has an obvious effect on motion in general. So the experiment. So the system in this experiment was the paper ball, and then the surroundings in this experiment were the gravity and the air resistance. And so this is basically the experiment here. We had the axis, and we threw the ball straight out instead of like up or down, because it never explicitly said that it needed to be an upwards or a downward like parabolic motion. And then this is the data that we collected and then threw into Excel to make the graphs. So step by step, we took a recording device, which in this case was just a phone, and we set it up facing a wall like seen here. A video was then called the ball being thrown straight outward in a half parabolic motion. This video was then uploaded to Tracker, in which the position of the ball over the time was able to be like plotted, and then data was able to be created. This data was collected, and then graphs were then made in Excel, and then we went to GlowScript, and then we used a computational model to kind of describe the same experiment, and we took that computational data and plugged it back into Excel, and then compared the graphs with drag and without drag. And then that's what it says here, is compared to the experimental data. So data comparison. So right here is our real data, and you could see that it ends roughly around like that, right past like the 1.5 range. So the computational model we made without drag, which is seen here, which simply just has the force of gravity and then the position or the velocity update and the position update. You could see that the x value is very large compared to this one with drag, because drag is working in the x and the y. With drag, you can see when the drag was included right here, we had to use different equations and stuff that GlowScript had in order to convert this into something that we were able to make FNet, which is gravity and drag, and then plug that into the update formulas. But you can see that the x value in this case is much more similar to the actual data than the one without drag. Possible error. So any type of human error, whether it be rounding error or coming to guess and check with like a b value, all that is possible error. The angle of the phone, you can see back in the picture, the angle of the phone was slightly downwards, so that kind of made it hard to plot on the x-axis. The shape of the ball, so there could be certain parts of the ball that had more surface area, which made the drag or the air resistance like act more on that part. And then how the ball was thrown. So if it was thrown like downward with a force or upward with a force, it made me hard to make it like, or maybe hard to tell like the initial velocity. So those are all possible errors. So the what if / what does it mean? Do any of these models predict the terminal velocity? So as you can see here in the velocity in the y direction, you can see that it's like a parabolic shape, and in this case it is accelerating. So this is not terminal velocity because it's accelerating through the ground until it hits it. And then in the x direction, you can see this is much more linear shape, so it is not going to accelerate anymore. It is like the fastest it could be. So this would be like a more accurate representation of like a terminal velocity. And then straight up versus projectile throw in respect to time. So the formula for time is 2vi over g times sine theta, no matter where you're at. It's just when the ball is thrown straight up, there's a sine factor of 1, because 90 degrees, sine of 90 degrees is 1. But any factor that you get less than 90, or any number that you put less than 90 as the angle, the factor is going to get lower. Therefore, the time is going to be lower. And yeah, that's about it. Thank you.